I usually start lectures by saying, any questions?
What kind of universe do you talk about?
Well, I was listening to you people talking about universes, and it seems to me that there's one possibility that is so simple that people don't discuss it. Because certainly a question that occurs in all religions is who created the universe and why, and what's it for. And one thing that preoccupies me a little bit is the question of why do things exist? And I think the answer is that that's an extra hypothesis that doesn't make any sense. See, it's all right to say, does this class of water exist? But if you ask, does X exist? That means, is X one of the things in the universe? So to say that the universe exists is silly, because it's saying the universe is one of the things in the universe. So there's something wrong with that idea. Well, if you carry that a little further, then it seems to me that it doesn't make any sense to have a predicate like, where did the universe come from, or why does it exist? So another view, which might be related to the famous many worlds theory, is that this is just a possible universe. And there are lots of possible universes, and there isn't any reason to say that this one is distinguished, except that we're in it. So if you think of a computer game or something like that, here's a little sequence of reductions. First, imagine that there's a computer that simulates some little world, and there are people in it, and the people are pretty smart. We'll talk about how they could get smart later. And after a while, one of the people asks the other, why are we in this world, and where did it come from? And of course, they're fooling themselves. There isn't any world. It's just a simulation. Somebody wrote the program. But if they got that far, then they could say, who wrote the program? Okay, now step two is, suppose somebody wrote the program and didn't run it. So there's no computer. Well, still, once you've written a program, and let's say a description of the computer it runs on, then everything that happens in that world is determined, and the computer and the program logically imply what people will be in it and what they'll do and what they'll ask. And so all of a sudden there doesn't have to be a program, it's just a possible computation. And then the next step is you don't even have to think of it. There is such a computation. So anyway, the question is, getting back to our universe, what's going on here? Why is the universe we're in the way it is, whether it exists or not? And now there's this famous thing called the anthropic principle, and some physicists take it seriously, and some think that there's something wrong with it and they shouldn't think that way. But clearly we couldn't ask that question unless our possible program that we're running had certain properties. And one of the properties that you need to have an intelligent creature is that well, we know how we got here in this universe. We evolved. And you can't evolve unless you have self-reproducing machines, or approximately things like something like DNA or RNA in some way to copy it. And there are other constraints on the universe that come from the anthropic principle. You couldn't have a Guth-like universe where suddenly things are exploding and creating stuff. So you can't have too many bubbles. Or, in fact, I think you have to have something like conservation laws, because if energy weren't conserved, then every now and then some configuration would appear and everything would blow up. So the real question is why the universe has to have laws at all, I suppose. But one thing I've noticed is that when physicists try to explain to the public, this is the old days before things got sophisticated, they would make a great fuss about how what they call the uncertainty principle and so forth, and they'd say, the world isn't the way Newton described it. Things are probabilistic and indeterminate. And the curious thing is, it seems to me they very rarely mention the opposite side of that. The reason why Pauling was so interested, being a chemist, is that nobody talks about instead of the uncertainty principle, I'd like to call it the certainty principle. If you take a Newtonian solar system, it won't last, or at least if it's a big complicated one. Jerry Sussman and John Wisdom once simulated the outer planets for a while, and they decided they were stable for about at least 3 or 4 billion years, but it looked like the orbit of Pluto was chaotic. They didn't simulate the inner planets, and for all we know, or for all I know, it might be that the influence of Jupiter and Saturn, which are really big, are enough that at some point in that time maybe the Earth will get enough energy to be thrown out into space. But generally, in classical physics, you can't have things like atoms with things in orbits that stay there a long time. And it's only... So what I'm saying is nobody explains to the children in grade school and high school when they talk about quantum mechanics that in fact quantum theory is why things are so stable and certain. They'll emphasize that if you had a DNA molecule, there's a possibility that one of the carbon atoms will suddenly tunnel out and land in Arcturus. But the fact is that at room temperature, a molecule of DNA is good for several billion years, and that's one of the reasons why evolution is possible. So it's sort of interesting that in communicating with the public, most physicists are so entranced with uncertainty that, have you ever heard a physicist explain that quantum mechanics is why things don't jump around? It's sort of a funny thing. And I think this question of why the universe is the way it is, if you think of a collection of possible ones, is maybe we should take the anthropic principle more seriously and say, if you're thinking of various models, which of them are stable enough to support the kind of evolution that we know took the order of a billion years. Apparently the first cells appeared pretty quickly after the Earth got cool enough. I think I've heard people estimate that it's less than 100 million years. And then it took about 3 billion years to get to really good cells, that animals and plants appeared about 400 or 500 million years ago, and then things took off very rapidly, but evidently it was a long period where nothing much happened. Anyway, somebody asked, what about intelligence and emotions, and why don't we have... It's a completely different subject. Why don't we have good theories of what the mind is and how it works? And I think in the last few years, some people have started to get good theories of the nature of thinking and so forth. Before computer science, there weren't particularly good theories. It seems to me that to understand something like a brain, you have to have hundreds of concepts like data structures and different kinds of memories and so forth. And if you look at psychology, it seems to me it has a very strange history. There are a few thinkers like Aristotle who sort of start out with some pretty good and pretty bad ideas about psychology, and then, as far as I know, nothing happens. The ideas of Aristotle in the book on rhetoric seem to me about as good as the essays by John Locke and Hume and the English philosophers, even Spinoza, so that a couple of thousand years elapsed without any progress in psychology. And although physicists started up around that time, with Galileo, and we've had 3 centuries of rapid progress in physics. It seems to me that psychology didn't start till around 1880 or 70. That is the first recognizable idea that the mind is some sort of mechanistic system, and you can make theories and try to predict them and do experiments to confirm it, is barely a century old. And even that stuff didn't make any progress till around 1950, when we started to see cybernetics in the 40s and artificial intelligence in the 50s and 60s, and something called cognitive science starting to appear in that same period. So a mysterious question is why didn't science have ideas about thinking until recently? So we don't really know very much about how the mind works because the history is so short. My favorite example, I think, is that in the 1930s, late 1930s, a botanist named Jean Piaget in Switzerland started to observe his behavior as children and taking notes and asking them questions. And in the next 10 years of watching these kids growing up, he wrote down several hundred little theories about what sort of processes are going on in their brain and how did each of them develop from some others and so forth. He wrote about 20 books on this stuff, all based on observing 3 children carefully. And although people nitpick about the observations he's made, the general structure seems to have held up. And strangely enough, almost all of the processes he described seem to happen at about the same rate and the same ages in all the cultures that have been studied, which is a whole lot. So, but the question isn't, was Piaget right or wrong? But why wasn't there someone just like that 2,000 years ago? What is it about the nature of cultures and science and so forth that no one thought to observe children and try to figure out how they work? Because Piaget didn't need cyclotrons. What he used is glasses of water and pieces of candy, and make little shapes of candy of different forms. You know, sometimes you'd have 5 candies close together and 5 spread out. And children younger than 5 years old will very much prefer the ones that are spread out. The conjecture is that they're estimating size by the extent, whereas 7-year-olds say, oh, it's the same, I'll take these, I can, because it's easier to pick up. And, what happens between 5 and 7, and he tried to make some theories of that, and some of those theories were okay. Seymour Papert was a research assistant for him, and he had another theory which I liked better, and we studied some children. And anyway, the point is that theories of the mind are very recent. Psychology really went through many phases that we now think are very silly and shallow. But the reason for that was that people didn't have the ideas of data structure. There was something called mathematics, which worked very well for physics. But it turns out that the kinds of mathematics that developed in the years before computers were not good at describing in detail what would happen in a process that involved maybe a dozen laws. In physics, we're successful because we discover ways to account for very large classes of phenomena with just 3 laws like Newton or 4 forces or whatever, and the number of assumptions are always less than 10 or so. And then there's some chance that mathematics will give you ways to do logical reasoning and figure out exactly what might be consequences of those simple laws. But if you take 20 assumptions, mathematics is dead. There's a beautiful subject that both physicists and mathematicians love called group theory. And group theory is a little mathematical thing where you make about 5 assumptions. And from these 5 assumptions, you get lots of problems and theories that people spend their lives on. There are some problems in group theory that have been unsolved for 100 years, but there are many that have been solved. But my point is that if you make 5 assumptions about the same things, these assumptions are different, then you're on the edge of what people can understand. On the other hand, if you write a computer program to do something, and it has 100 lines of code, then we don't have any way to figure out the consequences of that in general. It's just too hard. And it seems to me that the reason why psychology didn't get anywhere until starting around the 1950s was that in the appearance of what we now call computer science, several hundred new ideas appeared that no one had ever had. So very often people think of computer science as the science of what computers do. And I think of it as quite different. Computer science is a new way to describe and think about complicated systems, and it comes with a huge library of new ideas. For example, sometimes I hear brain people saying, well, it looks like memory is located in the hippocampus. And then another one says it's not located in the hippocampus, it's only stored there for a little while, and then somehow it's moved into somewhere in the cortex, other cortex. The hippocampus has 4 or 5 cortexes of its own. And they talk about working memory and long-term memory and short-term memory. Now, even in the year 2002, most of those so-called brain scientists have never heard of cache. I don't mean money cache, C-A-C-H-E. If you buy a computer today, you know that it has a big memory that's slow, it's called hard disk or tape or whatever. Then it has another memory that's pretty fast called RAM. Maybe it has 1 million words of that fast memory, or 50 million now, since it only costs a few cents per megabyte, maybe less than $1. And the average computer also has something called cache for instructions, where it remembers the last few things it did in case it needs them to do again. Then it doesn't have to go and look somewhere else for them. It's got several kinds of cache. It has front-end cache and back-end cache, and I don't remember what those are. But the point is that in computer science, there are ideas about dozens of kinds of memory. There are dozens of kinds of ways things can be stored in memory. You can store them as if-then rules. If this happens, do that. You can store them as things called semantic networks, which are little pieces of information connected by links that themselves have properties. You can store things in what are called neural networks, which are like semantic nets, except that the links are dumb. This is connected to this one by a link that has some number like 0.7. Neural nets are wonderful for learning certain things, but they're terrible for the rest of the machine, because the rest of the machine can't figure out what the neural net knows. So some years ago, Papert and I wrote a book about the limitations of neural nets. But we didn't talk about the really serious limitation, which is that the more of the brain that is used to learn in that particular way, the less the brain will be able to think and reason about what it's learned. So one thing that we've learned in artificial intelligence or computer science is that there's some fast tricks which are sort of effective and useful, but in the long run they're dead ends, because the machine doesn't understand what it knows. And where am I going with this? What I'm saying is that we're in an era in which people have just started to get what look to me like pretty good ideas about what thinking is and how it works. And we're still burdened by most of the world having 100 or 200 year old bad ideas that the way thinking works is that there are ideas and they're associated with other ideas, and when you do something good, you're reinforced, and there are traces of that and so forth. So the world is really very thick with old pre-computational theories of how the mind works, and in some way it's almost harder now to get people to think about more sophisticated ways of representing knowledge and acquiring it. For example, when you learn something, the standard theory is if somebody gives you a reward, then you're more likely to keep it in memory. And if they discourage you or don't reward you, then you throw it away. But suppose I happen to do something that works. I find a new way to hold a screwdriver to get a screw in without the screw falling off. One of the troubles with screws is, or at least the old ones with slots, is that as opposed to the new ones with little crosses, is that they won't stick to the screwdriver. And but after a while you learn how to do that. What is it you learn? You certainly don't learn the exact sequence of motions. You learn some higher level representation, and we call that the credit assignment. If something works and you had to do 10 things in order to get it, what is it you remember? How do you figure out which part of your activity was relevant? In the old psychology theory, they had a simple idea. The thing you did last was relevant. But, of course, the thing you did last was put the thing down because it was fixed. So there's all sorts of new ideas coming out. What has not happened, strangely, is this. The first experiments to get computers or computer programs to simulate human problem solving actually started around in the early 1950s. I'd even say just before computers became available to the general public. For example, there was a early computer at Princeton designed by John von Neumann. Several copies of it were built. He was a mathematician who appears to be the first or second person who clearly had the idea of the modern computer. There was also a fellow in Germany named Konrad Zuse who worked out this idea, but he couldn't get anyone to pay attention to him. And the main idea about the main difference between the modern computer and the computing machines that had come before is that the old computing machines could perform the same kinds of operations. They could add numbers, they could store things here and there and get them out again. But what they did was determined by a fixed program, usually by a set of punched cards, which would say first do this, then do that, then do that. Maybe if this happens, use this deck of cards. If that happens, use a different deck. So that was the early computers. And what von Neumann and Zuse realized is that wouldn't it be better if you stored the program in the computer's memory just like the data, and then you could have, they were thinking of the future rather than the present, and then maybe someday the computer could compute a new program for a new job and store it, and that made the computers more powerful. And in the early 1950s, for the first time, computers got enough memory so that there was actually room to store new programs in them, and some pioneers started in 1954, 5, 6, started experiments where they actually wrote programs that wrote new programs that would then run. And this led to the development of certain languages which were very good at writing, in which you could write programs that would write in the same language so they could keep changing. There was a lot of progress, and by 1960 we had two major languages which were good at modifying themselves. Unfortunately, these languages were a little bit unfamiliar to other people who didn't see the great power of programs that could change themselves, and the world was overtaken by other terrible languages like the famous C language, or Fortran, or Algol, and so forth, which became universally popular and in which it's almost impossible to write programs that change themselves. That's just a parenthesis. Is it Bentham's law that says the bad drives out the good? Whose law is it? Gresham's law. In modern software practice, we see this. I can't understand why this 35-year-old language called Unix has suddenly become popular, but the only thing I can think of is that the other operating systems got filled with so much garbage in the intervening 35 years that nobody could deal with them. And it's not that Unix is the latest thing. It's the last fossil that hasn't completely dissolved from the past. So they're starting over, and as far as I can see, they're starting over to make the same mistakes. Well, in the early days of this thing called artificial intelligence, we started to try to make programs that would do very advanced things. Maybe that was a mistake. One of the first programs that I was involved with was a program that would prove theorems in Euclidean geometry. It just crossed my mind. I'm curious how many children learn Euclidean geometry anymore. What Euclidean geometry used to be was a rather amazing subject where you would learn a dozen assumptions, like that 2 points determine a unique line, or if there are 2 lines, then they're either parallel and don't intersect, or if they intersect, they just intersect in one place, and that 2 triangles are the same in all respects if they're the same in 2 sides and an angle between them, and so forth. Euclid, I don't know when the hell Euclid was, probably 600 BC. This was a wonderful subject because you were in a world where assumptions were very simple and there were only a small number of them, and you used a logic which was very clear, and so it's a beautiful thing, and you get all sorts of interesting truths and falsehoods, and you can check them and so forth. For some reason, a large fraction of humans find it very hard to deal with a subject where you don't have to know much. It's a great mystery to me how you can be bad at mathematics when mathematics is the simplest of all things. Yet you get people who get high grades in history or social sciences where nobody has the slightest idea of what's going on, and you can't understand anything. That's a side subject. How could a person be bad at mathematics? It must be that somehow they get a wrong model of what the activity is. I remember once trying to tutor a student who couldn't prove theorems, and I said, "What's your trouble?" And he said, "Well, I think I was sick the day that the teacher explained how you prove theorems." So this poor kid thought that there was some special way to do this. Of course, the way you do it is by using general common sense knowledge of figure out what, if 2 things are related, which one is causing the other, and that sort of thing. And in fact, when I told the student that there wasn't any known way to do this yet, he brightened up and got better at it, because he really seemed to think there was something he didn't know that he needed to know, and that it wasn't a matter of drawing on the general resourcefulness that you'd expect every normal person to have. If you didn't know you're supposed to be a little bit original, maybe it's hard. Anyway, I was fussing with geometry a little bit, and I wrote down a draft for how would you make a program that would, in fact, take some statement in Euclidean geometry and find a proof for it. And that was in the late 50s. And by 1960, a little group at IBM Research managed to write one of these programs that, in fact, was pretty good and could compare pretty well to a high school student's ability at that sort of thing. Shortly after that, we had a student who wrote a program that solved symbolic problems in calculus, integral calculus, and it did it well enough on an old computer that it could get an A in the MIT first-year calculus course. Of course, it couldn't do the word problems, but it did quite well in calculus, and we told it about 50 or 100 little rules of thumb that you use in different situations, and worked very well. So here we're aiming at what's considered to be fairly high quality of human performance. Before long, in fact, that program had evolved into a computer that was better, into a program that was better than any human in the world. And there was a commercial version of that program called Maxima, for Project Max Symbolic Mathematician Program, which in fact put a lot of mathematicians out of business who had been involved in trying to find new ways to integrate functions. It's an exciting story. But it couldn't do word problems, so a couple of years later, one of our graduate students decided he would try to get a computer to solve less formal problems, like John was 4 years older than Joseph when Joseph was twice as old as John had been 10 years ago. Most high school students, I don't know if that's a real problem, but most high
pi years old.
Right. But most, even high school students have considerable trouble with that. If you can get your head clear, which is hard, you end up with two equations about John's age and the other guy's age, and the two equations are different, and if you're lucky, they have a unique solution. And this program was able to take pretty complicated English sentences and figure out what equations they were talking about and solve the equation. If it was about anything else, it couldn't do anything, and we tried to improve that program for a while, but it was a dead end in the sense that if you asked the program to do anything else, it didn't know what the words mean. So people started to use computers for other specialized problems, and by 1980, we had tens of thousands of programs, each of which was quite good at doing some very special thing. But there was no program that could do the kinds of things that you'd expect your 5-year-old to do. In fact, 5-year-old can beat you in an argument if you're wrong enough and the kid is right enough. To make a long story short, we've regressed from calculus and geometry and high school algebra and so forth, and we're trying to get people to work on common sense problems like the sort that every 4 or 5-year-old can do. And what's interesting is that although there are perhaps 100,000 people writing expert programs, maybe even 1 million around the world, expert specialized programs, I've only been able to find about a dozen people so far in the world who are interested in trying to do simple, everyday, common sense jobs of the sort that all children can do.
Thank you.